Swayam Prabha. Digital India. Educated India.
So, unlike the coaxial nozzle, a discrete coaxial nozzle usually used to have multiple jets. They may vary from 3 to 4 or even more. They deliver a powder of stream towards the molten pool via separate nozzles corresponding to each powder stream. The inclination of these channels with respect to each other affects the powder flow characteristics and shift the location of powder stream's focal point related to the laser beam in both across the plane and along the plane of deposition. So, in that case, this is for example considering a laser beam at the center. Now, instead of having a cone of the powder flow like we discussed in the previous case, here in this case multiple nozzles will be mounted. So, this is for example a nozzle 1, this is for example nozzle 2, and similarly few more nozzles at the back. So, if there are 3, each nozzle will be at 120 degree apart. So, the powder coming out of these nozzles will get converged at a particular point, and that will be called as the focal point, and the distance from the nozzle to this point is called as focal distance. Number of powder stream channels that are participating in deposition has a significant influence on the stream characteristics and consequently on the catchment efficiency. So, few researchers have even demonstrated that if we increase the number of these powder delivery channels from 3 to 6, then the velocity of the powder coming out of the nozzle will decrease at the focal point. And due to the reduction of the velocity at the focal point, the particles will not bounce back here and there, and they will remain in the energy, either it is from the laser or it is from the molten pool for a longer period of time. Due to that, the catchment efficiency, the catchment of powder into the molten pool will increase with the same process parameters. So, as in this case again we are delivering the powder through a coaxial manner, but here instead of having a conical nozzle, multiple nozzles are used. So, it is basically an approximation of the conical nozzle, but there are few advantages of using this type of nozzles. So, before that, let us discuss a little bit about the design consideration for a discrete coaxial nozzle. So, for example, what you are seeing here in this diagram is a cross section of the discrete coaxial nozzle. Here, this diameter dn shows the diameter of the exit nozzle, and there are few nozzles like this around. Also, the RIN is the injection radius of the nozzle, or in other words may be called as the cone radius at this location. The ST is the standoff distance that shows the distance from the exit of the powder from the nozzle to the point where it is having or attaining, the stream is attaining the minimal cross section area or the focal point. This angle is phi, and that is corresponding to how much your nozzle is tilted from the vertical axis. This is by phi. So, now let us discuss about how these parameters, those are corresponding to the design or the geometry of the nozzle, affect different process parameters, such as the powder mass concentration, which signifies the number of particles per unit area at the focal length. So, if I just take this cross section, its top view will be something like this. So, how many number of particles will be there, that will tell us the mass concentration. So, if there are more particles in this cross section, of course the mass concentration will be more, and if it is less, the mass concentration will be less. This mass concentration, let me write it as Cm, is negatively correlated to nozzle exit diameter and injection radius. In other words, I can write that the concentration of mass is inversely proportional to the diameter dn, and also the concentration of this mass is inversely proportional to rin. It is obvious, as I increase the rin, this radius, right, the injection radius, what will happen? My stream will go apart, it will go away. In that case, this radius will definitely increase, this diameter will increase. As a result, the powder particles coming out of the nozzle will attain more area. As a result, less number of particles will be available in the cross section achieved at the focal point. In a similar fashion, if I increase dn, the diameter of the nozzle from which the powder particles are coming, then again this will result in having less number of particles per unit area. As a result, the same effect will occur at the cross section on the focal point. Hence, the concentration of powder particles will reduce. Also, the standoff distance, the SD, shows the negative correlation with the injection angle phi and the nozzle exit diameter dn. In other words, I can write as SD, this standoff distance, is also inversely proportional to the phi, and SD is also inversely proportional to the diameter of the nozzle. Let us try to visualize it. So, if I increase, for example, this angle, so increasing means, let me just increase this angle. So, here you can see the next axis which I made corresponding to the axis of the injection nozzle. You can see now this new phi is greater than this phi. As a result, the focal point will also move above. If the focal point will move above, we can see that the standoff distance will reduce. So, it is obvious from here that if I increase the value of phi, my standoff distance will reduce. In a similar fashion, if I increase the nozzle exit diameter, that is dn, in that case as well, my standoff distance will increase, and it is obvious again. So, if we observe that this diameter is increasing, right, hence in that case it will increase like this from here as well as from here. So, it is obvious in that case as well that my focal point will be at a level above from here. However, if it will decrease, definitely my focal point will be below. As a result, your standoff distance will decrease if you increase the value of dn. It is important to have a very optimal value of this standoff distance, because if the focal point is very much close to the nozzle exit, that means the less value of the standoff distance. In that case, the molten pool will be also very close to the nozzle exit, and the powder particles, fumes and the other undesirable things coming from the molten pool may affect the nozzle. However, if I have a standoff distance very large, in that case it may be in some cases beneficial to us also. However, it may not be sometimes desirable, as my focal point of the laser may not be achieved within that standoff distance. Therefore, we have to choose this standoff distance optimally based on two factors. One, the focal point should be sufficiently at a distance from the exit of the nozzle in such a way that it does not harm the nozzle due to the heat coming from the molten pool and the fumes and the powder particles bouncing from the pool. Also, it should be close enough that it falls within the range of the laser focal point or laser working zone. Also, it can be observed that this RIN positively depends on the standoff distance, or in other words, the standoff distance is directly proportional to RIN. It can be seen from here itself. For the same case, if for example, I just increase the RIN, meaning to say this point will move away like this, right? In that case, it is obvious now, and this is the axis of the powder you are delivering. You can see that this axis has been shifted like this downward, and obviously in that case my standoff distance will increase. Hence, if you are increasing the RIN, of course your standoff distance will increase. If someone is designing their own nozzle, they should consider these factors related to the geometry of the nozzle while designing it optimally. Also, we have to ensure that the overlapping area of the powder stream is always more than the laser spot size. However, it can be seen obviously now, if the overlapping area of the powder stream is larger than the spot diameter of the laser, then definitely I will not be able to catch all the powder, and hence the efficiency of the process will reduce. So it is inherent that we want the powder particle stream diameter larger than the spot diameter of the laser, but we know that if we do that, definitely we are going to lose the efficiency of the process. So that is why the DAD process are usually not very efficient in terms of the catchment efficiency of the powder. A lot of powder got waste during the process itself. So why it is really required? Let us try to see here. So as you can see here in this diagram, there are stream 1, stream 2, stream 3 and stream 4. They are getting merged and they are having correspondingly the overlapping area. Like in this zone, two beams are merged together, right? In these zones, two streams are merged together or overlap together. Where in these zones, if I consider this particular zone, three streams have been merged together, right? And in the center zone, four streams are merged together. So in other words, I can say the concentration of the powder particles in zone 4 is greater than the concentration of powder particle in zone 3, and it is greater than the concentration of powder particle in zone 2 and greater than the concentration of powder particle in zone 1. And you can see that here the diameter of the laser spot, let me write it as diameter of laser, it is greater than the diameter of the zone 4, as you can see here. So if the diameter of laser is greater than the diameter of the zone 4, in that case one can observe very interesting phenomena here. It is that the powder concentration is not uniform inside the laser spot. It is varying, because we have seen that the concentration is different in different zones, and all three zones are coming inside this laser spot diameter now. As a result, if I move in different directions, for example, I move in this direction A, B, in anywhere like this, that case the concentration of powder available in front of the laser, on the back side of the laser will be different, and hence your process will not be omnidirectional. And as a result, when you move in one direction, you will have different type of property of the material based on the geometry as well as the material properties, and if you move in another direction, different geometric and the material properties will be achieved of the deposit material. Hence this type of processes are not desirable. What we want to have uniform powder concentration inside the laser spot. So the desirable is shown here in this diagram. Now you can see we have stream 1, stream 2, stream 3 and stream 4, and they are all getting merged. They are getting merged in this zone. Let me rewrite it as this is the zone. This is the zone 1 where only one powder stream is there. This is the zone where two powder streams are merged, and this is the zone where three powder streams are merged, and this is the zone where four powder streams are merged. So you can see, if I consider this laser spot diameter, anywhere inside this laser spot diameter, the powder concentration is C4. It is everywhere same inside the laser spot diameter. Therefore, now I can move in any direction and the obtained property of the deposited material will be consistent if I move in any directions. Also, it is not only important to achieve the omnidirectionality, it is also important to achieve the correct stand of distance from the substrate. As for example, any change in the stand of distance induce a corresponding change in the overlapping area of the powder stream. It can be observed here. If I change minutely, for example, slightly stand of distance is changing, I have enough area surrounding this laser spot diameter which is corresponding to the zone 4 where all four powder streams are merged. So one can have now very important consideration here, that is corresponding to the stand of distance. The stand of distance should be very optimal, and we have already seen on what parameters it depends. It depends on the nozzle exit diameter, the injection radius, it also depends on the inclination angle. So all these parameters should set appropriately so that you get your standoff distance in an appropriate manner, and the diameter of the laser beam and the diameter of the C4 means where all if n number of nozzles are there, all the overlapping area of all the streams is almost equal to the cross section of the laser. However, one can notice that in that case lot of powder will get waste, because at the substrate, for example, this is the scenario which we are seeing, and in that case it will be very obvious that this much powder is going to be waste. So that will reduce our catchment efficiency. Another very important benefit which we see for particularly the discrete coaxial nozzle is its capability of manipulating the powder concentration even when the nozzle gets tilted. So this advantage of the discrete coaxial nozzle over a continuous nozzle one is the ability to manipulate the carrier gas flow rate and flow velocity for individual powder streams. So if there are 3 streams, I can control the powder flow rate in each of these streams, like let me call it as M1, M2 and M3. By appropriately controlling the flow rate in each and every stream, I can control the concentration of the powder stream even when the head is tilted. So a head tilt of continuous coaxial nozzle over an angle of assume 45 degree renders its non-omnidirectionality with increased density of powder on the bottom than the top, as you can see in this diagram. So if my nozzle is tilted, the powders under the gravity will come down. As a result, you will have more density of the powder particle or more concentration of powder particles at the bottom than the top region. As a result, if your laser is coming also like this and it is making a spot, there is no material available on the right side of the spot, while there is a lot of material available on the left side of the spot. As a result, the material property which you will obtain in the deposition may vary if you change the direction of deposition. But this is not the case if I am using a discrete nozzle. But because if I tilt the head in that case with discrete coaxial nozzle, the omnidirectionality beyond 45 degree can be easily restored by simply increasing the drag velocity of the carrier gas for the upper stream. For example, here in this case, if you see, the upper stream is number 3. So I can increase the flow rate of the powder in this nozzle. If I increase the powder flow rate in this nozzle, of course I can compensate and I will be having more powder flow rate on the top side and the less powder flow rate on the bottom side. As a result, the concentration of the powder available around the laser spot will be uniform. However, in both of these cases, let us now try to understand how the powder get interacted with the laser beam. So let us assume that there is a powder here which is marked as A, and it is on its path toward the center of the molten pool. Assume that this is the center of the molten pool. So this powder particle is moving towards the center. As it comes inside the laser beam, it got interacted with it at point X, and from point A onwards, the particle A strips a portion of laser beam's energy and directed towards the center of the molten pool where it is headed to already. So this phenomena of absorbing the energy from this region to this region by the powder particle and the Gaussian nature of the laser distribution, for example, this laser is TEM00. Of course, we know that the intensity distribution will be Gaussian. The intensity of the laser will be less at the periphery and more at the center. In that case, as a result, insufficient heating will be happening at the edge of the substrate, as you are seeing here, because anyway the energy was less available on the periphery of the laser due to the Gaussian distribution of the laser beam intensity. Also, in this region, basically the powder particle will start absorbing lot of energy, because at this point A, the powder stream is at temperature TA. As it comes into the contact at X, it will start absorbing some energy and its temperature will keep on increasing. So it will increase more energy on the left side than the right side, because its temperature is keep on increasing, hence its absorption of the energy will also keep on reducing when it moves towards the center of the molten pool. Due to the absorption of lot of laser beam energy by the powder away from its center, the penetration in the substrate away from the center will be less, as you can see here. and that is why this molten pool usually is having this kind of shape in all the DED based processes. And this results lack of fusion at the edges of the substrate and more fusion of the substrate at the center. This may result later on some defects such as porosities and all. Therefore, the central feed powder systems become a little bit popular. In the central feed nozzles, we usually have a powder stream at the center. So, this is my powder stream, and it is surrounded by a conical laser beam. And that of course reduces its diameter and got merged to a small diameter as well. Now in that case, the energy is more available on the corners and at the center as well. As a result, the energy on the substrate is available quite uniformly in that case. So this is the typical intensity distribution of such donut kind of laser at a particular height. If I go down, you can see the beam will keep on merging like this, and at the focal point it will merge like this. In that case, now we know that the larger intensity is at the center and powder is also coming at the center, so it will absorb more energy from the laser beam from the center portion, which is anyway was having more energy. Also, now as the powder is absorbing some of the energy from the center of the laser beam, the intensity will become quite uniform, and as a result you can see this type of deposition will be obtained by the ring type, by a ring type cross section of the laser beam. It is quite uniform in that case. Also, the powder particles, as they are coming now from the center, the catchment efficiency of the process will be higher. It has been observed that the coaxial nozzles recorded the efficiency up to as low as 30%, where the central feed nozzles, such nozzles where the powder particles are coming from the center, used to have the efficiency above 80%, because in that case the powder particles are enclosed by the laser beam, and that doesn't allow really a powder particle to bounce off or go away from the molten pool. Now let us discuss a little bit about some non-pneumatic nozzles for delivering the powder. First of all, let us discuss what is the need of it at all. The high velocity of the powder particle lead to decrease in powder catchment efficiency, along with a deteriorate surface roughness or the surface finish of the top deposited bead also. The use of conveyance and the shield gases increases the convective cooling of the molten pool also, thus creating high energy dispersion. So as we have seen already, many gas passes are usually used in the case of coaxial nozzle. For example, this is the coaxial nozzle we are having, and in that there is a provision for giving the shielding gas to protect the optics. There is a provision to give the shielding gas to carry the powder. There is a provision of providing the shielding gas to protect the molten pool from the atmosphere. These multiple streams of the gas will increase the convective heat transfer close to the molten pool. As a result, the gases itself will take away a lot of heat. So the dispersion of this heat due to the convective heat transfer is quite high in these cases. As a result, we have to provide more power to achieve the similar results. So usually when the powder particles come with the desired velocity from the nozzle, it impacts onto the molten pool. Due to this high impact onto the molten pool, it may be possible that the powder particles bounce back. They may not be trapped by the molten pool. Also, the velocity of the powder particles, those are coming at the center, are usually higher. Also, the temperature of molten pool is higher at the center. So the chances of absorbing the powder particle at the center are more as compared to the powder particle those are heading towards the periphery of the molten pool. As a result, the deposited bead looks always high at the center and less towards the edges. Also, it has been discussed in many of the literature that the involvement of lot of these gases, there is a possibility of entrapping these gases into the molten pool, which leads to increasing the porosity, consequently a decline in the mechanical property of the final part produced by such nozzles. This particular study by Wong et al. Shows that what happened if we use non-pneumatic powder delivery nozzles. For a non-pneumatic powder delivery nozzle, the sample cross section is having a better deposition rate with the same process parameters. That shows us the catchment efficiency of the process increases with the same process parameters. Here now we are able to deposit the cross section of 8.6 mm square, while in the case of gas assisted nozzles the deposited area is 8.09 mm square. So obviously the catchment efficiency is increasing in non-pneumatic systems. Also, the total number of porosities are going to be decreased in the case of non-pneumatic system due to less chances of entrapping the gases. Here it is 0.15 mm square, the total area of the porosity. While in the case of gas assisted system, the total area of the porosity was obtained around 0.040 mm square. Also, the significant improvement was found on the surface roughness. Why? Because I have already explained that the now powder particles are not coming with a very high velocity in the case of non-pneumatic systems. As a result, they may not be enter into the molten pool with a high impact and not leave their any impression behind. That is doing nothing but the decreasing the surface finish of the deposited track. In the case of non-pneumatic system, the surface roughness of the deposited track was obtained to be around 2.14 micron, while in the case of gas assisted system, it was 14.25 microns. So significant improvement was found on the surface finish side if we use non-pneumatic system. So it is desirable at this point of time, if you are studying an advanced course, that you learn about what is the future trend for these delivery nozzles. So that is going towards the non-pneumatic nozzles. However, before I start this discussion, I have not seen any commercially available powder delivery nozzle which utilizes the gravity based system. All these setups are still on the research level, but I'll just tell you some of the ideas that how one can deliver the powder particles towards the molten pool through a non-pneumatic nozzle. So the first one is a torsional vibration applied through an offset piezoelectric. So you can see that there is a tube here. On the periphery of this tube, there is a piezoelectric actuator is mounted, and if I give appropriate input to this actuator, it can move back and forth. As it is moving back and forth, it is giving the torsional vibration to this particular tube, and as a result the powder particles available inside will start traveling into this tiny nozzle and will get delivered onto the bed. This particular setup usually have the diameter of tube they have tested is for 50 and 125 micron. It's a very tiny tube, and the diameter of powder particle in that case varies from 3 to 22 micron of copper, iron and invar. The frequency they typically use in their system is up to 49 kilohertz. As a result, the mass flow rate of the powder particle coming out of this nozzle varies from 0.005 to 0.3 milligram per second. This is another possibility where there is a ring type piezoelectric here, and there is a tube, the glass tube filled with the powder particles. It is mounted on a column Z as you are seeing here. In that case, this actuator is going to give a vibration to this tube. As a result, the powder particles will start flowing into this nozzle. Here if you see, the tube diameter is approximately 1102 to 400 micron, while the powder particle size is varying from 14 to 72 micron meter. The frequency details are not given in that particular research, but the mass flow rate can be obtained up to 10 to 30 milligram per second. The another possibility is vibration through the water bath. So there is a sonotrode here in this system. As you see, this sonotrode generates the vibration, and that vibration is transferred to the medium, that is water here, and that further transfer this vibration to a tube here. As this tube got vibrate, the powder particle start flowing into it. Typically in such system, in the study of Yang et al., a tube of diameter 280 micron was used, powder particle of 12 micron was used, frequency of 20 kilohertz and mass flow rate up to 0.05 milligram per pulse was achieved. Next possibility is of utilizing the acoustic vibration. Here you see there are subwoofers here 1 and 2, and by giving appropriate input to these subwoofers we can generate the acoustic vibration into the powder tubes. As these powder tubes now will start vibrating, the powder will start flowing into these channels and deposit the material onto the substrate. In the study of Yang et al., they have used the tube diameter, in this case around 380 to 600 micron, and the powder particle size of 63 to 212 micron. They have used the frequency of up to 50 to 300 hertz, and the mass flow rate they used is 5.8 to 35 milligram per second. Another very simple possibility is by mounting the two piezoelectric, one corresponding to the vibration in this direction and one corresponding to the vibration up and down in this direction. When the appropriate vibration is given to these piezoelectrics, two piezoelectrics, the powder will start flowing from the powder delivery tube. Here in this case, the tube diameter is 200 micron and 350 micron, while the powder particle size is 10 to 90 micron, and the powder was for soda lime and the stainless steel in the setup of Zhang et al. Also, they have used the frequency of about 20 kilohertz and the mass flow rate of 1.25 to 5.8 milligram per second. This one is the concentric laser beam system for a powder delivery. Here you can see that the laser is at the center and the powder is delivered from the side like in a cone. So, very conventional system which is very much popular in the additive manufacturing also is described here for delivering the powder by gravity or vibration. Here you can see there is a central piezoelectric here. This particular red color material is nothing but the piezoelectric, and if required this piezoelectric actuator can move up and down like this. When the appropriate vibration is given, the powder particles will start flowing through this cone and deliver the material towards the molten pool. The tube diameter or the channel diameter in this case is around 600 micron and the powder particle size is 45 to 150 micron. They have tested, the Wang et al. In 2011 have tested it for stainless steel and Invar. They typically used a vibration of 20 kilohertz and they are able to deposit the material with a flow rate of 120 milligram per second. So, this is very much promising system and already available non-pneumatic system for delivering the powder in the powder feed based additive manufacturing system without using any carrier gas.
So let us have a look at a DIY where we will see how the powder can flow under the influence of gravity when an additional power source such as vibration source will be assisted to it. You know that when the powder is stuck into a tiny orifice due to the jamming effect, it can only flow if a vibration source is additionally provided to it. As you can see, when the motor touches the tube, here the powder is starting flowing and it is delivering the powder towards the required portion which could be a molten pool. This small experiment you can also perform at home. Here the powder material is stainless steel. As soon as the vibration source is moved away, you can see that it immediately stops flowing the powder from the orifice. Such systems are very popular for delivering the powder precisely towards the molten pool. Though it can be noted that such a commercial system is not yet available, though many laboratory setups are available.
So, with this it completes the different types of powder handling systems in the powder feed additive manufacturing. Let us summarize our discussion so far in this slide. So, here I am trying to show you the effect of different process parameters. Like first one is the powder injection angle. We have seen that a low powder injection angle supports a longer depth of focus consequently promoting an increased range of passive stability and high deposition efficiency. So this angle was, if I just want to recall you, this is the laser coming from the center and this is the cone angle, right? This particular angle was phi. So if I decrease this angle phi, of course my focal point will go down, and as a result I will be able to increase the passive stability and high deposition efficiency. The mass flow rate of the powder particle coming is often associated with increasing the surface roughness and track porosity. So we have to be very optimal by making a compromisation between the deposition rate and the mechanical property of the final track. Also we have discussed that a lower powder velocity used to increase the catchment efficiency. It has also been seen that the reflective materials such as aluminium and copper are difficult to process using the conventional IR lasers as compared to shorter wavelength lasers. The melt pool size for conductive materials such as copper attribute to its high thermal conductivity, and it's fairly small, thus necessitating a smaller focal point of powder stream if you are dealing with the copper like material. Also we have seen that the stream characteristics at the focal point follows the Gaussian trend, and it validates the 1 by square rule of determining the size of focal spot. Ideally, the spot size of the powder stream should be smaller than the melt pool's dimension to ensure the high catchment efficiency, but we know that if we reduce the powder spot diameter lesser than the laser spot diameter, the process may not remain omnidirectional and we may not be able to move in any direction. We have also seen the effect of shield gas. The primary job of shield gas is to prevent the melt pool from oxidation. Often an additional provision of shielding gas provided for protection of the laser optics from metal fumes and powder particles. Omnidirectionality. The lateral feed nozzles are non-omnidirectional and primarily find application in cladding of rotary components where you are depositing just only in one direction and you are not changing your direction. But if you are going to change your direction, the omnidirectional nozzles such as the coaxial feeding, discrete coaxial feeding, discrete laser and the conical laser are preferred in that case. Smart powder delivery nozzles are required to be developed in future. Those are consisted of a closed loop feedback control with multiple inputs to adjust its feed parameters in accordance with that of the system. A gas-free powder delivery is nowadays required to be developed. Since the use of electron beam required a vacuum environment, the carrier gas cannot be used for powder feedstock handling. This necessitates the development of gas-free delivery nozzle to be used in conjunction with electron beam as a heat source. Now let us discuss a little bit about different type of systems. Those utilizes the 3-axis CNC machine, 5-axis CNC machine and robotic arm, and definitely use metal as a raw material. So the first popular system I am going to discuss about is by Optomec. In their system, they used to have the laser of around 400 to 3000 watt and they are using IPG fiber laser. The diameter of the melt pool they are able to obtain is from 0.3 to 5 mm. The spot size is approximately, the spot size at the focal point is 0.67 mm. Their deposition head is a continuous and discrete nozzle with gas delivery system which can deposit the material with 0.5 kg per hour. They used to have two systems, one is called as open atmosphere and another is called as controlled atmosphere. In the open atmosphere, the melt pool is protected just by the shield gas. But in the case of controlled atmosphere, the entire machine is purged with the organ and the entire system is controlled by the inert environment. Here the benefit is, if the powder particle, those are not able to stick to the mold pool or not able to contribute in deposition or got spread it here and there, you may be able to recollect those powder particles and process further. But if you are using an open environment machine, it will be difficult because the powder particle itself, when they come into the atmosphere, the oxidation occur on the powder particles, those got spread it here and there in the case of open atmosphere machine. Also, they used to provide the hybrid and standalone additive manufacturing system. the hybrid system has a provision of milling the component immediately after deposition. This summarizes the parameters available for their machines. The next is by the DMG Mori. In that case, there is a video shown here on the right side. They uses the laser of power up to 2.5 to 3 kilowatt. The laser spot diameter is 1.2 to 3.6 mm. Laser head is integrated to the headstock of a 5-axis CNC machine. And these heads are usually integrated with the ATC of the CNC machine. They utilize a continuous coaxial deposition head because in their case they do not tilt the head, instead they tilt the component, as you will see very soon in this video also. The build rate is approximately 2 kg per hour and the inert gas used to protect the molten pool is argon. They utilizes the 5-axis deposition and the work volume is also very large. It is about 2.6 by 3.8 by 2.9 meter. They utilizes hybrid with additive manufacturing station. That means their machine is capable of performing the milling operation as well on the same system. So as you see here now, the head is still vertical but the table has tilted. And as the table has tilted, in that case, the overhang feature is realized now. So after deposition of the inside hub, it will be finish milled on the same machine by utilizing a milling operation, as you see here. And after utilizing the milling operation, on top of this hub, the blades are deposited. And finally, on the same machine, by replacing this additive manufacturing deposition nozzle by a milling cutter, the impeller can be finish milled or the object can be finish milled to get the desired shape. So this is the system of DMG Mori. In a similar fashion, there is a system called beam developed in Strasbourg, France. They uses the laser of power range up to 4 kilowatt and the other parameters corresponding to their different model are shown here. Their build volume used to have lot of options on the X and Y axes correspondingly. They uses the 5-axis CNC machine with the Siemens controller. This is a system which uses the robotic arm, and if the robotic arm is used, the head has to be tilted in that case, and we know that if the head is going to be tilted, coaxial nozzles may not help. Hence, they used to prefer a 3-jet powder delivery nozzle. So this is the deposition nozzle mounted on a robotic arm, and right now it is not tilting the head because it is building just a vertical object, but if required it can be tilted, and as a result it will be able to deposit the overhanging features. So this summarizes different type of systems available, like by DMG Mori, Optomac, Formaloy, Instack, the Strasbourg, the Trumpf and the Max Root Tech and DM3D. They all used to prefer to have the CNC machine or robotic arm having the axes 3 or up to 5. Also, they all used to have either the diode coupled fiber laser or the fiber lasers, because these lasers used to give the wavelength of around 1 micron, and that is very much essential for processing the metals. Now I will just tell you briefly an innovative way of realizing the overhanging feature which I have found in one of the literature. This innovative idea of realizing the support material in lens machine of Optomac was once proposed by Schillinger in 2000. He proposed to use powder of the parent material as a necessary support for the structure. So let us consider now that we want to build a cube, and this cube is something like this, right? And of course there is a hole here. Assume that there is a hole here. Now how can we build this large overhang? Even if we talk about the multi-axis kinematics, making this part or closing this hollow cube by this horizontal wall will be very difficult task. Otherwise, because in that case there may be a possibility of collision. So what he proposed, that you build the part up to this, what you are seeing in this diagram. Once you build part where up to there are no support is required, definitely there will be no issues. And now if the support is required, we will fill the area where there is no material to support the overhang feature by the powder itself. So what we'll do, we'll just switch off the laser and just feed the powder into the cavity. So this is the feeding of powder into the cavity. So now what it will look like, a bed of powder after filling the cavity. Then you switch off in the next step the powder delivery nozzle and only keep the laser switched on in that case, and then sinter the top layer. Do not melt it, just sinter it. If you sinter this top layer, it will form a solid support at this region, and that will be having loose powder inside, of course. Now as a next step, we can further switch on both laser and the powder and continue our deposition on the top. Now what will happen in the end, you are able to realize a solid structure, overhanging structure without any solid support, while the support here is the loose powder. The loose powder can be later on removed very easily by blowing away the powder from the cavity. As a result, he is successfully able to make the ducts as you are seeing here. Those are having rectangular cross section and hollow inside. There is no material here inside. This type of structures are still very difficult to obtain even by multi-axis. The purpose of showing this example here is to show the innovative way this author has utilized the machine to make the overhanging feature instead of depositing the material on multi-axis kinematics. So with this, thank you very much. In the next lecture, we shall discuss about. Thank you very much.